Okay, you're welcome back to today's lecture too. In our previous lecture, we were able to look at the EMF generated by a DC generator. And from there, we started to look at the various types of DC generators. We first of all tackled the separately excited DC generators. And then from there, we went to the self-excited DC generators and we were able to discuss the shunt DC generator as an example of the self-excited DC generator. Today we are going to continue by looking at the various types of self-excited DC generators. So the next self-excited generator we're going to look at is the series generator. So when we say something is connected in series, I hope you understand. They are connected in line. Okay, there's no branch. So the same current is going to flow through them. That is it when we talk about something is connected in series. When it's connected in shunt, then you know that there's going to current division. But in series, the same current is going to flow through them. All right. So in this case, we are going to connect the field circuit. You see, in the shunt, we connect the field current, the field circuit in parallel. Okay. But in the series, we're going to connect the field current, this particular circuit, to be in series or in line, so that the same current is going to flow through them. So let's look at the circuit. So this is the armature resistance that we have. Now we have the variable resistor. Okay, so this is the variable resistor that we saw here. Okay, so this is the variable resistor that we saw in the case of the what we call the shunt generator. Okay, here we are taking the whole of this circuit and we connect it in series. This time there will not be any branch, as we see here. So this particular circuit represents the field that we are now connected in series with the armature circuit, so that we can get our terminal voltage or our terminals connected this way. So now let's look at how this is done. The field windings is connected in series with the armature windings that we call series DC motor, because the field is in series with the armature. Shunt because the field was connected in parallel with the armature windings. So take note. So the whole armature current flows through the field windings as well as the load. So now you can see that if you look at the current that's going to flow through here, the armature resistance, the same current is going to flow here. The same current is going to flow here. The same current is going to flow through the circuit, because there's no branch to cause any current division. So we can say that the armature current is the same as the field current, which is the same as the load current. IS, we are using IS to represent our field current. Sometimes you can use IF. It's the same thing. So the same current that's going to flow through. That's why we say that it's in series, because the same current is going to flow through. So we call it series DC generator. I hope it's clear to you now. So now let's see how we can come out with the terminal characteristics of the DC series generator. So now we can say that the difference between this voltage, ideally this voltage should have been equal to this voltage, but because of the drops over here, there will be a drop across this particular resistor. Now current flowing through this resistor to there will be another drop here. So in series circuit, there are going to be two drops. One drop because current will flow through here. The IR, the Ohm's law. You know that Ohm's law states that V is equal to I multiplied by what? R. Okay, so this IA going through this RA will cause this voltage drop. There will be another voltage drop also here. The same IA going through this particular resistance. So we can get our formula to now be equal to. So if you're able to get the drop here plus the drop here, now we subtract from the drop here, then we can get our VT. So we can get our VT formula to be equal to VT to be equal to EA minus IA RA minus IA R S. Okay, let me use the word S, or the letter S rather, or S, FS, the same thing. You are representing the field. So now you can see that this is the how the formula is going to be. IA RA to be this drop. You know that the same current is going to flow through this circuit. So IA RS. So now since IA is common here, we can factor IA out. So in that case, we get our EA to be minus IA into brackets. Now our RA plus RS. Okay, because we can say that now we have one resistor here, and you know that the same current is flowing through them. So if you add these two resistors, then multiply by the current flowing through them, then you get a total drop. Okay, that is how it's done. I just expanded it to get the drop here plus the drop here. But since the same current is flowing through them, we can add this resistor to this resistance, then we multiply by the current here. That is how we are getting this particular formula. So that's how I just proved it here. So now we can say that our VT is equal to EA minus our current, the same current that is flowing through these two resistors, or these two resistors multiplying, adding, then you multiply by this current, then you subtract from our EA, then you get the VT, the terminal voltage. So that is it for this particular formula also. So take note. There's no need for us to find field current here, because here the field current is going to be equal to the same IA, because the same current is flowing through the circuit. So take note of the series. Please, these formulas are very, very important. In exams, we will give you questions, and then we expect you to solve them using these formulas. So depending on the type of generator that we give to you, then you have to get the appropriate formulas. As usually, if you're able to draw the circuit, then you can come out with the formulas. Forget about this LS. This is to represent the windings, the inductor. Okay, the inductance. Okay, this is something different that we'll talk about later, maybe in this course. Now let's look at the terminal characteristics of what? DC generator. Okay, so for the DC generator, when you start DC generator at no load, there is no current flowing. So there will be current to create this magnetic flux. Okay, so we don't start generators, DC generators at no load. We connect a load before you can start a DC generator, so that there will be amount of current flowing to create the magnetic flux. Apart from DC generator, other generators you can start them off load, but DC generator we always have to start it on load. Now we start it on load, then as the load increases, then more current is going to what? To be drawn. So as more current is drawn, then it means that there will be more magnetic flux also. And the higher the magnetic flux, the higher the internal generated voltage. And there's another school of thought that will say that the higher the load current, the higher the armature current. Hence, there will be higher drops. So when you bring the two things together, then you see that the terminal voltage is going to increase, then get to a particular point that we call saturated point, where the voltage is going to work constant. So no matter the load, the voltage is going to work to be constant. Either you increase the load or whatever, the voltage is going to be constant. We call it saturated maybe volume. So we will talk about that maybe as we move on in this course. Okay, so at no load, there is no field current, so VT is given by a residual flux. Okay, when it says residual, they are flux that are being stored in the machine. So load increases, the field current rises. Okay, because the load current is the same as the field current, because it's connected in series. So as the load current increases, the field current also increases, because they are the same. And the armature current is the same current, because they are in series. So EA rises rapidly. Okay, since the flux increases, because of the flux formula that I showed you in the previous slide, because of this formula, as the field current increases, the field current is proportional to the flux. So as the flux increases, E also increases rapidly. So now let's see what happens. Then IA into bracket RA plus RS bracket close drop goes up to, now the EA is increasing. This drop is also increasing. So at the end of the day, what happens? But at first, the increase in EA goes up more rapidly than the drop rises. So from beginning of the motor or the generator, the EA generated because of the EA increase as a result of the increase in flux becomes more or rapid more than the drop. So this is how the graph is going to be. So that I see that the terminal voltage was increasing. Then it will get to a point that VT decreases. After a while, the machine approaches saturation and EA becomes constant. So as the machine increases, then VT decreases because of the IA, this particular drop. Then it will decrease to a point that then the voltage becomes constant. So no matter the amount of load that you connect to it, the voltage is never going to reduce, it's going to be constant. So that is the characteristics. So we can see the lower or the horizontal axis IL into is equal to I is equal to IA because they are in series and all the currents are supposed to be equal because there's no branch. So now that is it for the series motor, series generator. Now there's another generator we call compound generator. Compound generator. That's the last type of self-excited DC generator that we are going to talk about. When we say something is compound, we are talking about a generator that has some of two-fold windings. Okay, it combines the construction of the series and then the shunt. It combines the construction of the series and then the shunt. It has some of the field windings in series and some of them too in parallel. It has two field circuits, one connected in series and one connected in parallel. Okay, so we have two connections. Okay, so let's look at the compound generator and see. So as I said, it combines the two connections, the series and then the shunt that we have discussed so far. There are two set of field windings on each pole. One is in series and the other in parallel with the armature. A compound wound generator may be short shunt. Only field windings is in parallel with the armature circuit. Long shunt. Shunt field windings is in parallel with both series field and armature windings. This is used to overcome the effect of IARA and decrease of pole flux with armature current. So based on the fact that it becomes difficult to maybe control the field flux in series because the load current is directly the same as the field current. So we connect it in series. So we have one that we call short shunt. Short shunt means that only shunt field windings is in parallel with the armature circuit. Okay, only for shunt, only the parallel one is in parallel. Okay, or the parallel windings is in parallel with the armature windings. And then we have the long shunt. The long shunt meaning that the field windings is in parallel with both series field and what armature field windings. So take note of that. So let's look at the construction and we see how we can deduce the various formulas and then see what we can do. So for the short shunt motors, we can see that with the short shunt, we have the armature circuit, and then from the armature we get the parallel circuit before we get the series circuit. So we must have this branch before we get the series circuit. That's for the short shunt. Okay, don't forget that we have two field circuits. So this one field, there's another field over here. Okay, one is connected in parallel, one is connected in series. So the one that we get the parallel connection before the series connection, we call it short shunt. Okay, so let's see what we can derive in this particular type of what arrangement. So we can see that with this particular arrangement, our IS, that's the current that's going to flow through the series circuit, is equal to the current that goes through the load. Take note of that. And then we know that our IA will be equal to the amount of current that flows through this full circuit plus the amount of current that flows through this full circuit that also extends to the load circuit. So our IA is equal to IF plus our LS, or we can use IL in place of the ls because these two values are the same. Okay, because of this branch, this one is equal to this plus that because of the current division. Take note of that. So to get this our field current if, one way that we can get our field current is to subtract this from this particular current. If we subtract our load current from the IA, we can get our field current. Or we can use circuit analysis and see how we can come out with the field current. We can see that our field current will be equal to VT plus IL RS all over RF. Why are we getting that? Now, if we use the Kirchhoff voltage law, we can see that the voltage here, is equal to the voltage drop here plus the voltage that we get here. I hope we are getting the concept. According to the Kirchhoff voltage, the voltage law, the voltage that we get here, let's say our V F is equal to the voltage drop here. Let's use the I L R S plus our V T. The voltage that we get here, because the current flows here, there will be a drop here. Then that drop plus what we get here will be equal to this particular voltage. Then what is this voltage? This voltage is the current multiplied by this resistance. The current flowing here multiplied by this resistance. So we know that I F R F will give us this particular voltage and is equal to this particular parameter that I have enlightened over here. Now, if you want to get F, what do? We divide both sides by RF. So if you divide both sides by RF, this RF and then the one we are dividing here are going to what? Cancel. This and this are going to cancel. So what you're getting is IF is equal to ILRS plus VT all over RF. That's what we are getting over here because of the voltage, the Kirchhoff voltage law taking this particular loop. All right, I hope it's clear. So how do we even get our terminal voltage? So we want to get a relation between the terminal voltage and then the internally generated voltage. What's the relation? So now we can see that the relationship between this terminal voltage and then the internally generated the terminal voltage will be that. Let me clean this so that we can continue with our analysis. All right, so we want a relationship between the terminal voltage and then the VT. When the load increases, then because of that formula, we'll be able to then analyze it very well. So the EA, the internal generated voltage here, we can see that there's a resistor here. So whenever the current flows through a resistor, there will be a voltage drop. There's another resistor here, so there will be another voltage drop here. So if you subtract this voltage drop plus this voltage drop from this voltage, then we get our VT. But how do we get this voltage and this voltage? This voltage drop here is equal to IARA. This voltage drop here is equal to ILRA because this current is different from this current. This current, when it gets here, it will divide. Some will pass here. The remaining one that passes here is what we call IL or IS. So we use this particular current and multiply by this resistance to get the voltage drop here. So we can come out with this formula. Now, taking this big loop, according to the Kirchhoff voltage law, now we are taking this big loop to do our analysis. In that case, you'll be getting our EA minus this IARA minus ILRS should be equal to the VT. Because what is coming here, some will drop here, some will drop here, the remaining will be what you get here. So if we're able to get this drop, and we subtract from the amount here, then we can get our VT. So that is it for this particular terminal voltage formula. So take note of how we got the IF and VT. You have to also always have that one in mind. So that is for the short shunt. Now let's look at the long shunt. Long shunt means that this time around we are having the series circuit first before the parallel or the shunt circuit. Don't forget that in the short shunt we are having this here. Okay, in the short shunt we're having this field circuit, the whole of this here connected here. So we're having it as what? A short shunt. But now, because it's found over here, because it's here, we call it a long shunt, because this particular circuit, the parallel circuit or the shunt circuit, is far away from the armature circuit. So take note of that. Now let's see how we can come out with the relationships too. So this time around, we are saying that IA will be the same current that will pass through the RS in this particular scenario. In the previous one, we saw that the RS was the same as the load current. Over here, the RS will equal to the IS, the amount of current that will flow here, will equal to this particular current. Now, when it gets here, when the current flows and gets to this junction, there will be a division, current division. Some of the current will pass here, some of the current will pass here. So if you want to get the load current, then we have to subtract this particular current, the field current, from the one coming here, then we can get the load current. In the other way, the load current plus the field current will give us the armature current because of this junction. So let's see how we can deduce our formula once again. So we can say that our IA is equal to IL plus IF. IA coming here is equal to the one that goes here plus the one that goes here. It's just like a river that split. If you want to get the amount coming, then you have to go and look at the two split, add, then we get the amount of current, water that got to the branch or the junction. So that is it. So that's according to current, Kirchhoff current law. Okay, we are just applying Kirchhoff current law, Kirchhoff voltage law, and then the Ohm's law. That's all the three laws we are using in this circuit analysis. Okay, so you have to make sure that you understand this principle: the current law, the voltage law, the KV or the KCL, and then the Ohm's law. That's all that we are just applying. Okay, so take note of that. So now let's see the voltage law. In the voltage here, the terminal voltage here, we're going to use the Kirchhoff terminal or the voltage law. Now let's analyze this one. The amount of voltage that we can measure at this terminal will be equal to this particular voltage because there's no resistance here, so there's no voltage drop here. So the amount of voltage that you can measure across here will be equal to the amount of voltage that we can get across here. So how do we get this voltage across here? Okay, we can get this voltage across here when we know the drop and the drop here. Then we subtract from the internally generated voltage, then we can get a terminal voltage. So let's see. Now our internally the terminal voltage is equal to the internally generated voltage minus. Now we add this resistance to this resistance, then we multiply by the current that flows through them, because the same current that flows through them, and we know how we able to get this in the series generator analysis. So knowing that IA multiplied by into bracket RA plus RS minus, we subtract from the EA, then we can get our terminal voltage that we can measure at the terminal. Okay, this is the voltage that is being generated within the generator, and this is the voltage that we can measure at the terminal, because there will be some drops across the windings, because the windings, I said, are not perfect conductors. There will be voltage drops, they have resistance in them. Take note of that. So that is it. So now do we get the field current also? Okay, we know that the first field here will be the same as the IA. We are not interested in that particular current. We are interested in this shunt current, the current that will going to flow through the shunt resistance. Now we know that the voltage here is the same as the voltage here. So if we take our VT divide by our RF, then you can get our IF based on the once again the Ohm's law. We know that V is equal to I R. So if you want I will be equal to V over R. And what is our V here? Here we are using our VT because the VT, this voltage, is the same as the voltage across here. And what is our R? Our R is the RF that we are using in this particular analysis. Take note of that. So that is it for the compound. So now if a compound generator is given, there are two ways you can analyze it. If it's a long or short, then you see how to analyze and get the various formulas out of it before you can approach the question. So that is it. So now let's see the efficiency of a DC generator. When we talk about efficiency, we always say that no machine is 100% efficient. So what makes it not 100% efficient? Because of the losses. So how do we calculate for the efficiency? The efficiency of an electrical machine is the ratio of the output power to the input power, and it's usually expressed as percentage. So if you take the output power, the amount of power you are getting as your output, over the amount of power you are giving, you are inputting, multiply by 100, then you get our efficiency. So the input over output multiplied by 100 is equal to the efficiency. So what is our output? The output is the input minus losses. If you input something and you don't get the same thing as your output, then it means that your input minus what you are losing, then you get what you get at your output. So take note of that. So that is it for the efficiency. So what are the various losses in the generator that will not make the generator 100% efficient? There are so many types of losses in electrical machine. Okay, a generator is a machine for converting mechanical energy into electrical energy. And a motor is a machine for converting electrical energy into mechanical energy. I've already explained this. When such conversion takes place, certain losses occur within which are dissipated in the form of heat. Okay, so now if you input a particular mechanical energy and you don't get exact amount of energy as your output, there will be some losses. So what are some of these losses in there? We have number one loss in the electrical machine we call copper loss. And when we say copper loss, what is copper loss? It's the loss as a result of current flowing through a resistance. So it's I square R and it's in the form of heat. Okay, so copper loss due to I square R heat losses in the armature and the field windings. So there will be heat in the armature and there will be heat in the field windings because current flowing through a resistance will dissipate heat. So the heat given out, that's why electrical machine or generator or a motor, when you start it for long, you go and touch, it will be hot because of this particular loss. We call it copper loss because of the copper windings, the loss in the copper windings. There's another loss that we call core loss, and it's due to hysteresis and eddy current loss in the armature. Okay, so this is another type of loss, and we call this one core loss. It's in the core of the device. So we can reduce this by lamination, using soft core, and then the rest. Okay, so that is it. Now, the next is friction and windage loss. Due to bearing and brushes contact, friction losses due to air resistance against moving parts. Okay, you know that the electrical machines, the DC machines, they are moving machines. Whenever there is a moving object, there will be some sort of friction and windage. Okay, there will be friction in the bearings. There will be friction as a result of the brushes, so that the brushes are connected to the commutator. So as the machine moves, there will be friction because of the brushes connection. Okay, so take note of that. So the brushes contact losses between the brushes and the commutator. So that's the brush contact loss. So all these losses account for the general machine losses. So take note of that. Sometimes they will not give you maybe the copper loss, but they'll give you the total resistance, the total current. So you have to know this formula and calculate for the copper loss. For the other losses, probably you give to you, okay, because there's a way that we can calculate for these particular losses. So I would like to end here. Maybe this is all about the electrical maybe the DC generators. We have looked at all the DC generators, okay, the separately excited and then the self-excited. We have also looked at the types of the self-excited. We have looked at the various losses in the electrical machines. So in our next lecture, we will now solve more questions, and then we'll move on to electrical or DC motors. We are done with DC generators. So until we meet again, this is Akanyele Bismarck. I wish you all the best, and I urge you to observe all the safety protocols and then stay safe from the COVID-19. Goodbye.